Don't give anybody that.
I think we. What? Do that.
It's not possible. You just not you curve the question.
I'm interested.
Okay, everybody, how's it going? Yeah? Okay. The weather is almost beautiful, right? I mean, it is beautiful, but it's almost, well, okay, okay, you have shorts on. So you must think it's thin.
I'll tough it out.
You're toughing it out? Okay. Administratively, there is an assignment due on Friday. That is your outline. And I am sorry, I'm going through the pre-proposals, and there's some good ideas and some practical ideas that are coming out, but I haven't gone through all of them. So I'm inviting everyone to go ahead with your submission on the preliminary outline. It's, there should be no simulation in this preliminary outline, right? And it can be bullet points. You don't have to have, at least in the outline portion, right? But I do want to hear some thoughts from you about what you're planning to, do with the simulation. Yes, you have a question?
As far as if we haven't gotten to our project yet, but we thought about it and it seems like it is too difficult, are we allowed to change it? Or
Absolutely. I'm sorry, I interrupted you. What were you going to say? Anything else? Yeah. Okay. Yeah. Please change the topic if you think that it's too complicated or not complicated enough. And I'm working on the feedback. I will get to it, and you'll get like a page from me, just kind of describing some thoughts in terms of complexity and hypotheses that you might think about trying. Okay. Remember, there's supposed to be hypothesis-driven projects. I'm sorry, your name is it? Naya. Okay. Okay, great. Other questions on the outlines? Yes.
Okay, so
Anthony.
Difficulty-wise, that obviously depends on your willingness to make it difficult, and then also your ability to handle it. So what's your recommendation for? Okay, so for example, if we're testing a hypothesis, we have to change a parameter to see how that affects the simulation. But what's your recommendation if you have multiple parameters?
So okay, that's a great question. There are a lot of things there. So one, yes, difficulty is going to be dependent on a lot of factors. When I was an intern, there was this person who told me there's nothing that brute force and ignorance cannot solve. Okay, of course we don't believe that. It was kind of a joke, right? nonetheless, ignorance, not just like what you're willing to put into it, but ignorance can also lead to undesirable complexity and difficulty, right? So hopefully we can have, I know there are a lot of you, there's one of me, there's two TAs. Hopefully we can have a little bit of a dialogue, or a little bit of back and forth with the feedback that I'm trying to get to you all in terms of what I think is going to be difficult about it. Nonetheless, if you don't have some type of idea how you're going to do the simulation and you're writing it up, it may just be too difficult right now. Right? So you want to have, or if you can't find some example that's something kind of similar out there, or a capability that people leveraged in ANSYS in the past, it might be a little bit out there. Okay. In terms of number of parameters, that was your second question, right? So at least one that you can vary. Okay, at least one. And if there are a couple, then yeah, that's fine. I mean, you could create kind of a 3D type of plot or a color, like a 2D color or whatever, but you could do a couple parameters if you wanted. Or you might even find that these parameters are not independent of each other. Like maybe there's an independent number or a dimensionless number that relates them. But like obviously, it's going to be a little bit of an art. Not obvious, I guess, but it's a little bit of an art, a little bit of like thinking about it, and maybe if you have questions, we can talk about it during office hours. Unfortunately, I have to run right after class today to get over to Livingston, but there are office hours on Thursday, and I have send me a message if you like in Canvas Inbox. Some people have been doing that, and I can kind of give back like tidbits of things that I'm thinking about. Okay, is that somewhat helpful? Maybe. Does anyone have like a prop? Does it? Oh yes, go ahead. And your name is
Sarah.
Sarah. Okay, yes.
I'm just really just like in terms of I guess in order to like show like progress in terms of like that we're working on the project. I know you just mentioned I guess a simulation that we didn't need. But like could we also like that like not like an entire simulation, but just like a small part of it if we started working on it? Or?
I mean, I would prefer that you've got well-written hypotheses and that you've kind of detailed other things. If you have your simulation working at this point and you're confident about it, the project may be a little bit too easy, actually. Okay, so, but maybe not. Maybe I'm wrong. I mean, if you've been putting hours and hours into it, but if you've been putting hours and hours into it, I'd kind of be surprised at this point. These assignments are, I'm not grading them that harshly, if that's the right word. I'm not being that critical. It's more about just making sure, first couple ones, making sure that you're like thinking about it, so that a week before you don't start thinking about it. Okay, does that make sense? And I think Professor Stinger's plan to have you do a simulation, have you show convergence, have you show all the data, right, before the final project is due, is for everyone's benefit, except for those who have to grade it. It leads to better outcomes. Other points, other questions? Yes?
For the project outline, you want to follow, you want to see this kind of work.
Okay, so that template's a little bit extreme, right? Try to use, I guess to give you an idea of, this was an outline that we had in our research group that someone had created. It was a little bit out, it was a little bit farther along and many, many, many more hours. But you can you can take it and slice out what you don't want and go from there.
Does the problem you're trying to solve, is that can just be like you're trying to prove something?
We're not going for a Nobel Prize here, right? So, and prove is actually a little bit of a strong word, right? Here, we're kind of like, we would like to demonstrate, we would like to support a hypothesis, okay? Or, right, it's much easier to negate a hypothesis, right, to disprove a hypothesis. And prove one, right? You only need one counterexample. Nonetheless, yeah, you should have a hypothesis that, I mean, I would reword it so that if you end up, well, not telling you to be unethical, but if, like, in this kind of situation, right, it's a report, it's a story, so you might want to put a hypothesis out there that you can support, and you might say, look, this is a common myth. This is going to be a hypothesis that we disprove, right? It's going to depend on your results. So you can go back and kind of shape the hypothesis appropriately. Or you can tell the story as you like, linearly, and then say, okay, no, we were completely wrong. Okay, yes?
So you said the outline can be as simple as, like a bulleted list of what's going on, or as complicated as like the template you posted?
So I would prefer that it's in a Word doc, or in a PDF, right? So don't just like, I mean, how do you say it? Appearance matters, right? So, and in this context, right? So like, it looks like you just slap it all together and it's like a notepad document, that's not gonna be great, right? So, I mean, the outline is there to help you. I would say use it, okay? And I know everyone uses Google Docs, just, I think at one point I started requiring a docx format, so just be aware of that. Because if you do it in Google Docs and you export it to docx, sometimes it doesn't come out quite right. Okay, so if you haven't used Microsoft Word, it may not be a bad opportunity to look into this way, and it looks a whole lot better. All right, and then you have the people who say you have to use LaTeX and overleaf, and we're not going that extreme. All right, so kind of maybe in the middle. Have you done LaTeX? You're smiling. No comments. Okay, no comment. You love LaTeX. Do you know what LaTeX is? Oh, okay. Okay, so there is something going on in your brain. Okay, that's good. All right. Just no comments. All right, great. That's fine. I had to do my master's thesis in LaTeX, and I chose to do my PhD thesis in something called LIX. Which is like a graphical, I don't know if this probably still exists, but I've been converted away from the dark side. Or from the light side. I've been converted to the commercial side. All right, here we go. Today we're going to talk about physics and coupling between them. We kind of already talked about the scientific method, so we'll kind of just breeze through that real quickly. And then we'll get to a discussion on writing for the final projects. And so the preliminary outlines are due this Friday. There's not a post-lab assignment due on Tuesday of spring break for sure. And there's not a post-lab assignment for this. Right, you got 2 now, where there's not a post-lab. That's good, right? So it's a good time to focus on your midterms and on for other classes and on the final project. Okay, and the new lab assignment was actually due for them it became available. You've had it up since last Thursday, so it wasn't up today, all right? And then we talked about the academic integrity stuff briefly, and then we had a little bit more discussion about that with the other class, and then you saw the message that I sent out. So if there are any issues, just please communicate with me. Couple physics. So, what do you think we're talking about when we say couple physics? Yes. Symmetry, okay. All right, I mean, I can see, what do you mean? That's one word for 2 words. So, what are you getting at there?
Force couples, like symmetric in a way.
Okay. Yeah. So, you've got to have conservation of forces or equilibrium in that sense, right? It could be dynamic or it could be static. momentum. Okay, yeah, all right. Other ideas? Yes, Rishi.
Is it where you're testing like several different physics topics, but they're all, I guess, dependent on each other? Like,
Yeah. Okay, so yeah, so physics topics, we might think of them as different types of physics or different types of domains of study. Okay. Yes.
Do
And
they
your name
involve,
again is
Ian,
Ian. Okay, yeah, Ian. Go ahead.
do they involve like a system of equations?
Yeah, so we do a lot of things that have equations behind them, right? That's pretty true. And often it involves equations from different physical domains, right? So we've talked, what are some of the domains we've talked about? Physical domains, or the physics packages, the physics that we've talked about with this one. Yes, Neil. Yeah, we talked heat transfer, right? The heat equation, that's a biggie. What else have we talked about? Yeah, Rishi? Okay, so we talked about kinetics, kinematics. Yes, in particular, talked about that in terms of particle dynamics, right? And the different potentials that are involved and satisfying Newton's laws. Others? Yes?
Fluid mechanics?
Yeah, fluids now. And your name is?
Kurt.
Kurt. Okay, thanks, Kurt. Yeah, so fluid mechanics, right? So maybe like because some equations are famous, right? You have Navier-Stokes. I mean, you have Newton's third law, you have Newton's second law. You have a bunch of famous equations there too, right? But then building up a little bit, you have something like Navier-Stokes, which has principles of conservation of momentum, conservation of mass, and then you also have like the heat equation, okay? And so yeah, coupling those two together, right? This kind of idea. Okay, we got Fourier's law. You know, we could say all kinds of jargony terms now, right? Because we're all cool like that at this point in the semester, right? So you know, you got Fourier's law, got heat equation, and then you've also got like Navier-Stokes and fluid mechanics over here, right? And so you could try to put them together, right? And today you're going to probably get bored, but we're going to essentially look at the different domains and how they influence each other. Now, what are the different types of, I mean, you already kind of said it, heat transfer, right? You talk about fluid mechanics, Newton's laws, right? Now, if you think about your curricula in mechanical or aerospace engineering, or whatever engineering you're doing, what are the different physical domains that mechanical and aerospace engineers put themselves in silos doing? I give you a hint. A lot of them are the names of your classes. Any ideas? Or is this too simple? I mean, you're now like juniors. We got some seniors, right? Did any of you like identify? Like, I'm a solids person. I'm a heat transfer person. No? I'm a, yes?
Electronics person.
You're an electronics person. Okay, so that's not really mechanical and aerospace engineering. No, that's good. No, you're a mechatronics person, right? That's what we say, plus a physics person, plus an electronics person, right? So you've got these different domains that you work in, right? And the idea is that in this class, right, we bring a lot of these different domains together so that you can simulate them and you can begin to see how they couple with each other. Just like, well, let's look at these two problems. The one on the left, all right, which is our turkey problem, was that a coupled physics problem? Was that a multi-physics problem? No, why are you saying no?
It's just like heat transfer.
There's just heat transfer. Wait. Okay. Yeah, so it was. Now what if we dig into what is H? the heat transfer the convective heat transfer coefficient. You're not wrong. I'm just saying you could look at this two ways.
Maybe like energy.
Well, what goes into convection? Yes.
Oh, it's fluid.
Yeah, it's fluid mechanics, right? So you've got, yes, we lumped it in. You're absolutely right. We said, hey, we need a temperature differential, right? And we have this H, all right, the heat transfer coefficient. And if we were to dig into it, we would say, oh, well, you know, that's really due to natural convection, the buoyancy of the hot air surrounding the turkey. And as it goes up, it's able to impart some of its heat to the cold turkey, right? So you could argue that we kind of started looking at coupled physics when we introduced just this term of H. Okay? And sometimes it's really useful to not waste your time, well, we're not wasting time when we do this lab. None of our labs are a waste of time, okay? We have a heated wire, right? And we have flow past it, and essentially we're doing this problem but backwards. We're seeing how much we can change the temperature of the air that's going by a heated wire. That's what you're going to do on Thursday. That'll be that and your reports will be your kickoff, your send-offs for spring break. So that's kind of, yeah, it could go either way. You'd be like, nah, you just give me an H and I've got a heat flux into the system and that's it. It's a heat equation problem, boom, one domain. Or you could be like, oh, what was going on with that H? And then it's a fluid mechanics. Okay, what about the one on the right? The flow in the pipe that we did. Is that coupled physics? Someone from, not Rishi, but someone in quadrant 2 behind Rishi. Any thoughts? Was this a coupled physics problem on the right? Yes, no, maybe so. Anyone? Quadrant 2? That's you guys. Yeah. Thoughts? Okay. Quadrant 1. Coupled physics or not coupled physics? I don't know if you're talking about this problem or something else. Something else? Alright, anyone? In quadrant 1, is this a coupled physics problem or not? On the right. Sure. Oh no, go over here. Yes, your name is John. Yes, John.
Yes.
Huh?
Yes.
Yes, and how so?
Because it's fluid dynamics and or so it's fluids and also I guess kinematics.
Okay. So kinematics describes the motion of objects, all right, and kinetics describes kind of the forces and the dynamical equations, Newton's laws that dictate the kinematics. Let's go on. I think we're getting there. Because, yeah, you could look at the particles, but that's really a fluid mechanics problem. If I'm like tracking particles and stuff and their trajectory, that's still all kind of fluids. How though, you said, let's say that you're interested in forces, John. How did that involve, how might that be a couple of problems now?
I guess it's particularly dynamics.
Okay, all right. Do you remember where we were measuring force?
It was like a shear force.
Yeah, okay, so we're looking at, yes, we spent a lot of time thinking about plates last time. And in this lab, right, you were selecting an area or a region, right, so that you could measure the the drag force on that step. Okay? So now, can you argue for or against how that might be coupled physics? Now, anyone? Thank you, John. Yes.
Could it be like solid mechanics? Because if you change the geometry of that stuff, then you get a different result of the force theory.
Yeah. Okay. Yeah. So one, you are as soon as you start to think about forces, yeah. I mean, fluid mechanics, you could say, of course I've got forces. I've got lots of forces involved. I've got control volumes. They are forces, right? And so, is it really a mechanics problem? I would say slightly. And we'll say, okay, that's coupled physics. That's fine because we're trying to figure out drag. And so if you're like doing an airfoil or doing something where you put an object in an external flow, and you can say, oh, that's kind of coupled because I need to integrate the stresses, shear stresses or normal stresses or whichever component of stress based on the angle of the particular point on the object might be as you're going around the profile. You can say, okay, I'm figuring out the forces there. Okay. How could you make this even more coupled, though, if you really want it? Like coupling between the mechanics and the fluids. Yes?
Could you shoot the fluid at a wall or a block and see how it accelerates?
See how the block accelerates? Okay. Or see how the fluid accelerates? Both? Okay, so that would be more of a dynamics. That's interesting. That's interesting. What could I do if I wanted to think about the fluid mechanics coupling, though? And, not though. And also. Yes?
Could you run turbulent versus steady state flow through the same pipe?
Sure, and that's still kind of more on the fluid side, right? And we got fluids. Like this problem, do we all agree this is a fluids problem? Okay. So then what do I do to make it more of a mechanics problem? Yes, Kurt. Not Kurt, you're Kurt. You're Con. Yeah, Con, yes.
You can simulate the particles going through the system.
Still fluids, still fluids, still fluids. That's particles. I want mechanics. I mean, people say fluid mechanics, fluids, dynamics. Yeah. I want to be more solid mechanics. Yeah.
Could you change the fluid?
Still fluids. Still fluids. I need to think a little bit outside the current region. Yes. Yes, exactly. All right, quadrant 2. Okay, so we're in the house. Okay, yeah. So what did she just say? And your name is Min. Okay, Min. So she said we could think about how that step deforms. The way we implemented it, there was no way for it to deform, right? It's a solid, rigid boundary. Okay? So what you could do, if you want to introduce more mechanics, is mesh that region. You could mesh that region and treat it as a solid and give it properties to see if those forces cause any deformation. So if that region were like soft rubber, that could cause there to be, or you would be able to see deformation more easily than if it's like a solid piece of steel. Okay? Now, here's the thing with coupling. And maybe we'll go to this. We'll go to this, all right? Because I want to, it's related, okay? It's a lot of words, right? So systems can couple with each other, okay? With mechanical forces, with heat fluxes that come through, with pressures, right? So you have either pressures or shear forces and on an object that has fluid flowing over it, and we're calculating out the lift and the drag associated with that. They can couple because geometry deforms, all right? Or there's some type of induced change in the geometry. What, if we go back to this example, what is scary about, or what would be some issues if I say, oh, that nicely drawn checked region, not checked region, hashed, cross, whatever, that place that I've now put solid elements in it. What would be kind of the not pros or cons, but what would be the things you would have to consider if I made that red region very, very soft? That I wouldn't have to consider if I had it as steel, like a hard steel. What's the difference there? Yes, Rohan.
Would like the shape change also change the fluid appearance?
That's right! Right? That's the issue, right? So if you start coupling, okay, so you could have one-way and two-way coupling. So you could say, oh, you know, these are the forces, I calculate my fluid flow, these are the forces on this region. Don't touch the fluid flow shut off. Put these forces on that deformed region, or on that region that's deforming, and I just look at how it deforms. That would be a one-way coupling. All right? So one way, I do the calculations in the fluid domain, and then I couple them into the mechanical domain, and I just look at what happens to the mechanical side. Two-way coupling would be what Rohan described here. Now I've deformed the geometry. How does that affect the flow? All right, and if I affect the flow, that affects the forces. And so you start going back and forth. All right, and this form of fluid structure interaction is very tricky to get right. Okay, so it's an active area of research. It's been an active area of research for a long time. And where are some other domains where you can think, or where are some other physical problems that you can think of where you have coupling or not coupling effects that are significant? Now think of applications. So we just did like a couple of examples here, but what are some applications where you might be interested in, or you have to think about coupling? Yes?
Resistance here.
Okay, resistance here, yeah. What happens there?
An electronic or electrical circuit problem in the heater and the heat transfer problem between the heater and the outside air.
Yeah. Okay, so there. So that's a couple of problems. Now, what about, how could that potentially be two-way coupling?
Does the electrical properties change temperature?
That's right. It's gentlemen. Yeah. All right, that's right. Okay. So yeah, so you get into these cycles, right, where they can start affecting each other and making the problem more complicated. Okay. Now, what's another example? What's another example of where you have one domain affecting another domain, and maybe it goes back and forth a little bit, or not? It doesn't have to. But what are some other domains that have trouble? So that wonderful sound we just heard, I don't know, it sounded like someone's dragging something, right? Oh, on cue, all right? So you've got, right, you've got some type of coefficient of friction probably, dragging, right? And then you've excited some type of resonant frequencies or some type of resonance, right? And then that affects the jumping up and down of the object relative to the ground, and so it might actually become easier to slide as you do that. Okay? That could be an example of that. I mean, was that all mechanics? I don't know, but it was, you have some vibration and you have some mechanics and some contact mechanics. All right? What are some, you could even say acoustics if you want, but I don't think acoustics is really going to affect. I mean, that is definitely a coupling that people look at, is the acoustic output, and COMSOL does that really well. ANSYS, I'm sure you do it really well too, but I haven't played around with acoustics and ANSYS. but in CompSol I've spent some time on acoustics. What are some other examples of coupling physics? That was just a random one. How about some of you aerospace engineers? Any aerospace engineers in the house? What might be an example of coupled physics with fixed wing aircraft flying through the air? Fixed wing aircraft flying through the air. Are the wings really fixed? Yes?
You can analyze the fluid flow of the air around it and how the wing heats up as it accelerates, and if the motor like can stand it.
Yeah, so you could have, okay, so you could have some airflow over the wing, and that could affect maybe some of the heat transfer. If it's really cold outside, it could definitely affect some of your mechanisms. You could have some freezing and things. What else? If I'm thinking again of a fluid solids mechanics coupling more specifically. Yeah.
The wings like flex under the air.
Yeah. So the wings, the flex, maybe, right? So I've got that, and so yeah. So maybe I got a little slight change in shape, and then even more so, they can flutter, right? So they can start to vibrate. And that vibration can then go back and affect the fluid as it's going over, as the air is going over. And even worse is that if you don't have your wings tuned appropriately and you start inducing vortex shedding that has a certain frequency associated with the resonant frequency of the wing, you could start to have the wing be in trouble of failure because it's vibrating at resonance. Okay? So there's a whole field called aeroelasticity that kind of focuses on looking at the coupling between these aerodynamic flows and the elasticity of the objects. Okay. Any others that people want to share? Because I'm about to bore you with a bunch. Okay? Look at this. We're going to go through a table. All right. We have cause in the vertical column on the left, and in the horizontal rows at the top, we have effects. Okay? And so we're going to talk about how, and I have my cheat sheet over here, okay, to how we're going to talk about these things coupling with each other. And we have the opportunity to think about, okay, how does, let's say, we're talking about how does a thermal system couple to a thermal system, right? How does a thermal system couple to a fluid system? We go through this whole thing, right? And do you think that this matrix is nice and symmetric? All right, so does the solid fluid coupling, right? Is that going to be the same thing as the fluid solid coupling? It doesn't necessarily have to be. Okay. Oh, you're like, oh, sorry. So I mean, you can say in some meta. So this we'll see, right? Because we're saying one is the cause and one is the effect. All right. So here we go. Let's try it. How could a thermal system affect its thermal physics? Yeah, all right. Okay, and maybe I'll go back a couple of slides and say we're thinking about forces like heat fluxes, pressures, mechanical forces, stresses, whatever. Thinking about geometry. And also, I didn't highlight this, we can think about the properties of the materials themselves. I think Rishi was kind of getting at that, right? But you could have the viscosity of an oil change because of temperature, for example. Right? And we'll talk about that. Okay, so thermal. How can a thermal system influence thermophysics? Any ideas? Don't worry. We can have lots of wrong answers. We can have a few right ones. Okay. Yes.
Maybe like a phase change.
Yeah, that's a good one, right? So, I mean, you could argue that's like a solid going from solid to like a fluid, but yeah, you could have, as water is going to boil, for example, right? It's going to require that jump in enthalpy to get from the fluid state, or from the liquid state, sorry, fluid, they're both fluids. The liquid state to the steaming state. Yeah, that's good. All right, so, oops, those are some of my things from the prior one, all right? But you could have the change, the conductivity of the material can change, its heat capacity can change as well as a function of temperature, okay? Yeah, those are my scribbles from the previous class. I don't know, does it let me? It doesn't let me erase them. All right, that's fine. What about thermal fluid? What are some ways that you could have a thermal system influencing the fluid? I talked about one of these a second ago. Yes, Rohan.
Is it like the temperature affecting the solid?
Yeah, right. So temperature can affect the viscosity. Temperature can affect the density. All right. Temperature can cause the thermal expansion of a liquid that might be contained in a vessel. All right. There are multiple ways. Thermal system can affect the buoyancy, right? So it's the density, right? And that can lead to natural convection. Okay, so these are some ways that those systems can couple with each other. Okay, thermal solids. How can a solid depend? And this is almost like a hypothesis kind of thing, right? How do solid mechanics depend on thermal inputs? Yes, Ian, and then someone else.
Like thermal expansion.
Yeah, so just like we have thermal expansion with the thermal fluid, of course, the bar between two constrained walls problem that we cover in mechanics and materials that we love, right? That's definitely something that's fair game. What were you going to say?
No, it's just coffee.
It's coffee.
Yeah, sorry.
Oh, okay. You're allowed to cough in this class. That's fine. Okay. Anyone play with polymers and their glass transition temperatures? Yeah. Oh, okay, good. Isha, right? You're in senior's lab, right? So what do you care about with glass transition temperatures?
Like the temperature itself, or
Yeah. Or what are you playing with? You don't have to share anything proprietary, but why do you care about the glass transition temperature?
it has a lot to do with like how like the spray actually is. Like the spray will always spray like super specific like regime, and it's sprayed up to make overall glass transition temperature.
Okay. So you've got it. So you're saying that the spray mechanism, which is going to be involved, I guess, kind of the fluids level. All right. And if you've got a material that is maybe above or below its glass transition temperature, so typically above its glass transition temperature, it's going to be flowing more like a liquid, okay, and have a low elasticity to it. Whereas below its glass transition temperature, it will be more of a solid. Okay? And anyway, so there was a time I was working on hot embossing, and so like these methyl methacrylates, they have glass transition temperatures kind of like 90 to 110 degrees Celsius. And so you would kind of try to play with these different temperatures as you're forming the material, because you can obviously, it's more malleable, you can form it a little bit better when it's a little higher, but when you got to separate the mold from the part, you don't want it to get stuck. So you have to think about, okay, I cool a little bit, but when I cool, then I have like features that can get constrained about the mold, and then it can be hard to get to be molding properly. And you have changes in geometry as well, and changes in stickiness, and so all this kind of stuff is a thermal solid. So properties, we probably don't, I mean, you said electronics, right? But permittivity, and we talked about resistivity, potentially changing with the, someone mentioned, who said the thermal system with a heated wire? I'm not sure who said it. You guys? Okay. Anyway. Who mentioned the heating of wire earlier? Someone did, right? Me? Oh, shoot, I can't remember who said what. Okay, great. Okay. Fluid thermal, all right, we talked about how you can affect heat transfer, right? Based on the flow of the fluid, the fluid speed, the flow of the volumetric flow rate past the solid. That's going to potentially change the thermal properties, right? And I think I shared the story before where you have. Did I share this story where I had we were like driving in a car and someone wanted to keep their ice cream cold, and they thought if they stick it out the window and it was not below freezing outside, that would like help cool it. Well, no, right? I mean, you've got warm air, and you're introducing more warm air, and that can lose the heat more quickly. All right, fluid. How does a fluid couple to a fluid? Well, here we go. Fluid, you can have density that's dependent on pressure. Okay, right? So the air is a good example of that. Even incompressible fluids like water, they can change slightly in their density as a function of pressure. You can have gas and liquid interfaces. You can have liquid-liquid interfaces. You can have forces and these control volumes, and you can change the geometries as well. Going back to the fluid thermal and the thermal fluid, you can imagine that we also have two-way coupling there. As you change the density of material based on heat being applied to it, and then now you got to recalculate the flow. Right, you're going to go back and forth a little bit. Right, so there are two-way couplings possible as well. Fluid solid. All right, so you might have one-way coupling where we're measuring drag and lift coefficients. Okay, coefficients of drag, coefficients of lift on objects. Fluid electromagnetic. You could have flow of materials that you're introducing, and they could have different properties. So, like, I don't know, I can't think of a really great application here. I'm sure someone else can, but let's say for some reason that you want to have a really high capacitance, okay, between two conductors. You can imagine having a material, maybe some type of oil that has a high permittivity and flow between the two plates. And then you just said, well, that was one fluid, I had one block, and then right next to you had like liquid metal or something. Okay, I flew liquid metal in it. Right? And so you can like change the electromagnetic properties of the device based on the fluid you flow through. Yes.
The plasma we generate a fluid electromagnetic spectrum.
Well, is plasma a fluid? Yes, I would say yes, it is, right? Is plasma the fourth state of matter? Well, yeah, that too, right? But yeah, you can definitely see the plasma potentially affecting the electromagnetic properties, and we can see a change in the electrical impedance there. Okay, good. Solid thermal. So you can see that if you rub your hands against each other, right, that could create some heat through the friction. Okay? And you can see that, if I have two plates that that one's hot, one's cold, right? I can get heat transfer if I combine them or not. So solid mechanics. In fact, I showed you that system from my time as a grad student where we were trying to remove the bubbles, right? Everyone remembers that? Yes. I showed it, right? The spinning. Well, there's also another part of that system which I didn't steal, but another grad student in the lab had been working on these systems to heat and cool things quickly. So what we had, like using her design, we brought up a hot plate to heat up the mold very quickly. Actually, we brought down, I can't remember, it was a hot down. And then we would bring in a cold plate, okay, to be able to cool it. So you can do things like that in terms of using solid contact to dissipate or provide heat. Solid fluid, all right. So we have your pistons. You have you have your solid objects that are going to displace the fluid around it, and this is also an opportunity for two-way coupling. And you could also think that the geometry, how the nozzle is going to affect the flow as well. And like we said, we have the two-way coupling. You can go back and forth. We have solids that can affect solids. Affect the stresses, they affect the geometric configurations. We have solids that can affect the electromagnetic properties, right? So just building a capacitor, building a resistor, you're going to put different solids together for those different geometric configurations. And probably no one cares about how the electromagnetics affect the thermal systems, but if you have inductive coupling on your stove, that's a nice efficient way to be able to get heat from the electrical domain to your food. And we can use electromagnetics on magnetobiological or electrorheological fluids to change their viscosity or their elasticity based on whether the field is applied or not. You can also think about your motors, okay? Your DC motors, your AC motors. Those are ones that are going to be using electromagnetics to provide forces and torques. And then you can also use high E fields or high B fields to be able to change the electromagnetic properties of a solid or another electromagnetic device. Whew, we got through it. Some of you are still here mentally. Okay, thank you. So in the last little bit, we're going to switch gears. Okay, so what you're going to do in the lab? Anyone done the lab yet? Yeah, what did you think? Was it fun? Okay, it wasn't bad. Was it easy? Yeah, this one was like that. What does it entail? How's it relative to coupled physics?
Well, it's modeling the wire, the rectangle, and then it's seeing physics interact. So as you look at the velocity profiles, temperature profiles.
Right. Yeah. So essentially, what you've got, right, is you've got this is what it really looks like in real life. I don't know if that's real, but let's say you're looking at a wire. Okay, maybe this is better. You're looking at a wire like this. Okay, and we've got now air flowing past this wire. Okay, and we're looking at different temperatures. We're setting this. We're saying we can magically set the temperature of the wire. Okay, and this is the wire. And we can also control the flow rate. So we have the flow rate or velocity of the fluid going by. And what do you think? For a given temperature of the wire, will the heat transfer go up into the surrounding air at higher or lower velocities? Higher, right? It's going to be able to impart more heat to the surrounding liquid. Okay? So, or you're pulling more heat away from this hot wire. Maybe it's not a wire. Maybe it's a CPU, a processor of some sort. Okay? And so that's this showing this coupling between the fluid and the thermal domains. And the last thing that you do, which is for your deliverable, is you shut the flow rate off here. You say it's 0, and then you say, oh, we're just going to use buoyancy of the air to induce flow. And when we do that, when we introduce that buoyancy, right, that's going to be essentially natural convection. Has to be. Okay? And you get to see some cool flows past the wire. Okay? That's what this lab is about. Okay. So, science, experiments, and theory. We've talked a little bit about this in the past. The word depends is good for your hypothesis. Okay? So even though the feedback you might get on some of your preliminary outlines doesn't have the word depends in it, for me, I might say hypothesis-driven approach that discusses how the cross-sectional area is going to affect the drag force, okay, for flow, for some type of aerodynamic flow, okay. You can say, well, you can say that the drag force depends, my hypothesis is that the drag force depends on the cross-sectional area. And ideally you would say, and it's going to scale linearly. Typically not with aerodynamic flows that are real, besides laminar, then it is linear. But like over a sphere. But typically it goes with rho v squared times the coefficient of drag times the area. So you might say it's going to depend on the velocity squared, okay? Or something like that. It's going to depend on a quadratic relation. So that's what we're going for with your hypotheses. Make it testable, and then what are you going to do? You're going to test it. We talked about empirical studies in the past and how they can lead to data and information that then goes on to inform another hypothesis, or better yet, we go even further, theory. Okay? So a theory is something that it gets accepted after multiple experiments usually, and multiple supporting arguments and evidences that it does exist, right? So the point here, we discussed this previously, is that you had Kepler and a lot of other people doing empirical work, which then helped Newton develop the theory of gravity. I just finished listening to Stephen Hawking, Brief History of Time. And it was very interesting. The last chapter, like, he goes through all this stuff that I quite frankly can't understand or follow completely. And then the last chapter, he goes into something interesting kind of dynamics between different figures, including Newton and physics. It's an interesting thing. So without saying anything in particular about it, I didn't know some of the, and this is a classic. Have maybe read the Brief History of Time? Stephen Hawking? Yeah? Okay, what do you think? Huh?
In terms of what?
Like, did you learn anything? Did it expand your mind? Right? So black holes, the beginning, the end of the universe, a lot of things are in there, right? Anyway, so we then eventually get to sometimes we get to analytical solutions. Again, we've gone through this. And analytical solutions are nice because we can use them as baby steps, right? So what do we mean by baby steps, right? There's a question in when you're doing this outline, right? What are we getting at? What is one of the ways that you can have a baby step in your simulations? Let's say that you're trying to measure the airflow or the drag on an object, aerodynamic. What would be some of the baby steps you would employ for your report? Yes.
Simplify the geometry,
Yeah, simplify the geometry to what?
a shape that you can solve for by hand.
Yeah, at least that someone else has tabulated or that you could solve for by hand, right? So we'll do that. The next set of labs is going to focus on flow over spheres and cylinders and stuff of that nature, right? So that's not a bad place to start. You might also look at just like a block or a plate, right? There are calculations you saw in the dynamics section, right? Remember you used, hey, we have these different CDs for these different shapes, like for the balls, right, that were bouncing around. And so we just applied that drag coefficient appropriately to the model of particle dynamics. But here, and if it's an aerodynamic problem, you could consider putting that shape into your simulation and seeing if your results match. What is a good match in fluid mechanics? Good matches are different in different domains. I'd be ecstatic if I got my numbers to be within 10% in fluids. Okay? That'd be amazing. Right? So don't kill yourself. Okay? That's a general, all right, you know what I mean. Please don't do it, and don't overexert yourself for the problem if you're trying to get the last 10% in this class. If it's a fluid mechanics problem. Okay. Please do all percentages of your assignment. Okay, let's talk about writing. So there are different types of audiences, all right, that you're going to be writing for. The audience we care about here, unfortunately, is me and the TAs. All right, the TAs and me are the TAs and I are the audience. Okay. So what do you think this audience likes when I read things? What do you think I like? Yes, okay, Neil, yes.
Active voice.
Active voice, yes. All right, so active voice, and that's one of many things. Okay, clarity, and a good hypothesis. What is good, right? Well, it's something that we can test. And we are focusing on a genre that would be akin to something that you would find in a journal publication. So if you haven't read any dry journal articles or some very interesting journal articles, you might want to take a few minutes and read some. Okay? And if you want some recommendations, just go to different faculty in our department and read some of the articles they've written. You've got these faculty guest lectures, you could read one of them as well. Not just you've got to watch the videos and make comments, but you could go to and read some of their articles as well. Okay? This is just to help motivate us. Yes, we have grades. I don't like grades, but we have them. All right? I mean, I don't dislike. I don't like grading. Let's put it that way. All right? But I do like. Sometimes I like reading interesting papers, and I get inspired by what you write and the ideas that you put forth, because this is open-ended. So that is fun. Okay? But I still don't like assigning a grade usually. And then I just want to say something about the final project here. Okay, the final project video. It's 4 minutes in total length. 2 minutes should be some type of promotional video. Okay, so just be a little creative, all right. No one should get hurt in real life though, okay? That can be part of your creativity, but make sure no one gets hurt, alright? And then do like 2 minutes of essentially talking about your results, talking about your hypothesis, going through the technical. Any questions on that part of the problem? That part of the problem? We're going to talk more about, and just now, we're going to talk about how to assemble the final paper, and in particular, I want to focus on citations in a couple minutes. Okay? So, we need some type of testable hypothesis. Complexity is not a requirement. We need to have the ability to have a discussion, though, about what you're doing. Okay? At least you need to be able to discuss it with me in words. This depends on that. This depends on this. These are things that we have to consider. This is something we learned. This is something we expected. This is something we didn't expect. Okay? You could try to have complementary simulations with 3 different people. That is probably a recipe for disaster. It's often hard enough for one person to get a simulation to work, and then to have 3 simulations that are coordinated with each other, and 3 simulations where one result depends on the other, which depends on the other. Also probably not a great idea. So you gotta meld together, be reasonable. Hopefully everyone's doing simulations. They could be the same simulations. It could be someone having to sit there and wait for the simulation. Okay? Nonetheless, you are going to want to try to run things in a coordinated fashion. And we can talk about some of those things to consider. We are interested in this idea of the scientific method, where you have, yes, a hypothesis. Hopefully that is based on some type of observation, some type of discovery. And then you're going to go into your results, analysis, and discussion. Now, this is that chart again, and this is kind of the way that Professor Singer has outlined things. Notice, fluid does not have anything that should be done in 3D. Okay, pretty much. You see that? Thermal 3D, okay. Solid mechanics, okay, 3D. Even CFD laminar, probably not a great idea to do it in 3D. Okay? You can try. So, or cry, as Professor Singer has outlined here. Okay? But that, I think, is good advice. In 20 years, you'll all have such awesome computers that this chart will be antiquated. All right? Right now, though, I think this is good advice. Any questions in terms of the general idea, scope of projects where you might fall? Anything? All right. Here are some topic examples. Some people are doing stuff with balls. Some people are interested in doing things with heat sinks. Some people are doing some things with pipes, mixing. That's actually not really, no one's really done, maybe someone's suggested a mixer, but I haven't seen it yet. People are doing problems that are related to impact. That's tricky. We don't do a lot with LS-DYNA or explicit in this semester. Actually, I do like none. At least that's the current game plan. But it's out there, and you can do it. And if you look for some examples, you can play with that. But you can do many solid mechanics problems that are not using explicit dynamics. And then you have, of course, airfoils, and then you have some people who are interested in things like drag on objects. Okay, how do you write a paper? This is a short read, and I do suggest that you take a look at it, all right? It's by my postdoc advisor, and truthfully, this is how that research group runs. And it requires a lot of planning your experiments out so that you can write about them instead of just doing experiments and then trying to write down, right, select, down, select. Yeah. There's kind of two ways to do the research. You can go through this, and I suggest that you do, and you might even watch a video or two, okay? But what I want to point out here is that eventually you need to have references, okay? Eventually we need references. And this is now even more relevant with everything out there, like the generative AI and authenticity and integrity, okay? So let me just talk about how I suggest that you do references in the last 2 minutes that we have. I suggest that you use Zotero for this, okay? And we do give points, and we do evaluate how you acknowledge what's out there already, how you're acquiring knowledge, how you're learning knowledge. We want you to have references. One reference is not going to be enough, okay? So you need to have multiple references. So how do you do this? Has anyone used Zotero before? No? Okay. Well, if you can, so what I suggest is that you use it. It's completely free. Okay. And we have a group. If you want to join it, there are now 31 members. Okay. It's called 439 Multiphysics. It's a very original title. Okay. And there's a bunch of. Okay, good. Okay, good. It doesn't show detailed information of who's in there. Okay. These are some articles that people put in there. All right. And you're like, well, that looks really painful. Like, you're going to tell me I have to do this on a web browser. No, no, no. There are two things that you want to install on your computer. And since you've already installed ANSYS, many of you have, this is nothing like that. All right. This is like mini thing. If you're willing to install ANSYS, hopefully you're willing to install this. One is the standalone Zotero. I don't even know what they call it now. It used to be called the standalone thing. Right? This is the I don't know. It's a Zotero app, I guess. All right, and this allows you to not go to the web all the time. All right, like hardly ever. And it allows you to very quickly get a reference. So let's say that you I don't know. This is always dangerous. Let's say that you're interested in like ANSYS simulations of airfoils in turbulent flow. I spelled turbulent wrong. I know, you know. Okay? So maybe this is a reference that you use. Okay? What you do is you go into this standalone app and you go to the folder you want. So let's say that you're a 2025 team. So we'll say that we'll just add a folder for us. Spring 2025. And you're like, I don't know, A team. I don't know, right? Something like that. And so you're going to, you want to keep this as a reference to put in your paper. All you got to do is make sure you select it on A team and make sure you have the standalone, the embedded extension in your web browser. Come over here and you click this and it saves it to the A team, and now you've got the reference. Now it may not look perfect because it's not a web page, it's not an article, right? But you've got it nonetheless. If you go to Google, yes, you can use ChatGPT, right? But your references may not be true, okay? Right? It has, at least I think it's getting better, right? So let's say you want to do elastomeric airfoils. I'm biased here, okay? If you're interested in this, you click on this article, which again I'm biased and I think is quite good, and you come over here and you hit this little thing, and it takes it right to the A team. Now you're like, why do I do all this? Why do I care? Well, you care because now you can plop these in to your paper. Okay, so if you're doing it in Google Docs, whatever, I guess, but I suggest using Microsoft Word, but you can do what you want. So in Microsoft Word, ooh, that's not, I didn't want that to come up. Hold on a second. Let's see, we'll do a, blank document, all right? And let's say, this is a elastomeric airfoils are awesome, okay? And let's say I want to put it inside. All you got to do is come over here to this plugin, and you can add or edit the citation. I recommend IEEE, and you put in elastomeric airfoil, and it comes up in the 439, all right? Right there, it's there, okay? And I can like do, I like ANSYS, right? And I can do, again, Zotero, add, and we had like ANSYS airfoil, okay? I can put that one in there right like that, like this as well. Or maybe I want to go back and I want to put in two. I can add or edit the citation, and I can put another one. Okay, and it comes up, and I've already got this cited, so you don't have to duplicate, and then hit enter, and I've got a couple of them right there. And if I do 3, it does like 1 to 3. When you're ready, you can then type in the bibliography, and you can do add the bibliography, and there it is. That's it. Okay? Have you used this kind of thing before? Yes? No? Okay, yeah. You should have used it before. What do you all use? Mendeley, Zotero, RefWorks, EndNote. RefWorks, yeah. There are a bunch of different ones out there. Zotero is free and it's easy. We expect you to do this. Okay, to include your citations. What is this? We expect you to include your citations. And I think that Zotero is a nice way to do it. Okay? And this way it avoids any issues with questioning of where you got your sources. Any questions on this? Okay, please do this. We're evaluating the effectiveness of your ability to demonstrate understanding of the literature and knowledge, and acquisition of knowledge, using knowledge, citing knowledge. In the past, this has been a weak part of it. It's been a weak issue in the class, okay? So please make sure you use references. Okay. Well, that's about it for today. Any questions before we go? I guess I won't see you until spring break is over, so be safe, have fun, get some rest, and we'll do the attendance.